profesor yang mengajar environmental of engineering. Jadi beliau adalah sebenarnya adalah guru saya dulu. Jadi pembimbing S3 saya adalah beliau. Ya. Dan apa namanya? Saya harap kalian bisa mengikuti kuliah ini dengan baik. Dan saya mohon kalau ada pertanyaan jangan takut bertanya ya. Kalau pakai bahasa Indonesia nggak apa-apa. Nanti saya translate dalam bahasa Inggris ya. Nanti saya sampaikan kepada beliau. Baik, itu saja ya. I told the student if they have question, they can ask in English and I will translate it to you.
Okay. Selamat pagi. Good morning everyone. So I'm a professor in the University. I'm in charge of the Department of Environmental Analysis. Going to the environmental engineering. So today I'm going to give you just an introduction to the environmental risk analysis. So okay. So before the theory regarding the environmental risk analysis, I want you to introduce some of the incidents occurred in Japan. So maybe Japan is I think on the countries we suffered many environmental pollutions, and we have a very big history of the environmental pollution problem. So the first example is the in 1950 to 1960, it's long away. So, but we had the high economic growth period in Japan, and at that time, so companies don't care of the environment. They don't care of the environment, and so many people thought the economic growth is more important than the health of the people. So that's the error. But anyway, so we call the actual mining pollution incident. It started about the 1890, and we call it, this is the first, we call it just the origin of public hazard in Japan. First big incident in Japan. So, and then we have the very notorious four big pollution diseases. It's about 100 years ago, Itai disease, Minamata disease, and Niigata Minamata disease, and Yokai asthma. Do you know the name of Minamata? Yes. About Itai disease? Oh, really? You know? Itai, oh, really? So, I give you the. I think you may already know the detail about those diseases, but I give you just brief introduction of those diseases. About the astrobiological pollutions, so it is a pollution incident which occurred at Ashio Copper Mine. It's almost the center of Japan, and located around Watarase Gawa River. Not so clear photos, but it is near the Watarase River. And so exhaust gas containing SO2 from the mining plant and effluent water containing many heavy metals from the mining zone, and so the plant seriously polluted the environment around there and downstream. So you can, this is the photo of today. So the estate is about 100 years ago, but still mountain looks poor. So almost all trees died and not recovered yet. So And all mountains around there became bold crops using water from water Asikawa died, and the rice harvested there could not be sold because of the high concentration of cadmium. So many farmers must evacuate that areas and not recovered yet well. Now this place is become just like a museum of the mining zone and museum of the environmental pollution. So if you have you have the chance to visit Japan, it is also interesting to visit here. And this is the photo of about 100 years ago, and he is a very famous person who fight with government to keep the people. So maybe almost all elementary high school students study the history of his activities to keep the people, to protect the people. So should I use it?
Suaranya kedengaran.
Should I? Okay, so next one is Itai disease you already know. So Itai means painful. So Itai means painful. So the cause of this disease is also mining zones or mining companies. Mining companies discharge the wastewater contain heavy metals. People consequently consume the vegetables and water contaminated by cadmium. So, yeah, this is the photo of the women who are suffered from the cadmium. And yeah, every part is they are just pushed, and very painful. So they cry at the time. So they cried, uh, crying painful. So this disease is named Ita disease. So every part is painful. So this disease is named. This is the distribution of the concentration of cadmium in soil. Yeah, this is the concentration of the cadmium in soil, and this is the distribution of the prevalence of women over 49 years old. So it's almost the same. So people who live here eat the vegetable or rice in their houses, and they suffer from the cadmium pollution. And hepatitis is mainly just only for women. And hepatitis is mainly just only for women, not men. Maybe the difference of the metabolism or mainly because of the strength of the bone. But anyway, so almost all people who are suffering from cadmium, especially old women. And another one is Minamata disease, also very famous and notorious. And the cause of Minamata disease is the company manufacturing acetaldehyde discharge their wastewater containing methyl mercury into Minamata Bay. And mercury was used for the catalyst for chemical reactions. It accumulated into fish, and the local people consumed the polluted species. And yeah, it resulted in numbness, tunnel visions, and hearing impairment and death. So, and also, great tragedy is also the baby in mother's womb also suffered from that. So, even their mother is not suffered from mercury pollution, or they are not the Minamata disease, but the level of the mercury, when mercury is very high in baby, in wounds, and they just born with Minamata disease. So that's a great tragedy. And this is the fear of the food chains, main food chains, why methyl mercury is accumulated in the people. So I think maybe you know, so the cytogenetic mercury is accumulated in plankton first, and breed small fishes eat plankton, and also the concentration become higher, and also big fish eat the very small fishes, and concentrated more. Other people, if they eat fishes, the concentration of methanol is great. So they suffer from the Yamata disease. So the mercury, especially mercury, has the great effect to the sorry. Yeah. So the so methyl mercury also goes through the placenta. That's also a problem. We also sometimes people say they are the placenta barrier. So babies in wombs are protected from the pollutant because placenta barrier can work to protect from the pollutant in the mother body. But in case of the organic mercury, they can go through the placenta. And babies that they suffer from the pollutant, especially organic mercury. And also, the tragedy of this disease is so mothers, especially mothers, eat more fishes because they want to make their babies healthy and bigger and stronger. So mothers who are pregnant eat many more fishes compared to other just normal people there, and in result, so their babies got sick. So that's a sort of great tragedy. And the Niigata disease is almost the same. The company is different, but in other places we also have the Niigata disease. It's almost the same mechanism. From the chemical company, this product from the chemical company, the river water is polluted with methyl mercury, and they are getting Niigata disease in other places. And the Yokkaichi asthma is different. It's because of the air pollution. So the cause is oxides of the sulfur and the nitrogen. We call it the salts or NOx. Released from petrochemical complexes in the atmosphere. And the local people inhaled the polluted air and were suffered by cough, sputum, and bronchitis and asthma. Anyway, so they cannot breathe so well. So this is the photo in 1960s, about 10 years. So you can see the maybe the length or distance you can see about the several tens meters because of the air pollution. And when I was a child, I saw this town from ships, from a ship just near this town, and I was very surprised. It's a great memory for me, but I was very surprised because this city is surrounded by orange color, just like gold. It's just a morning. So it's before the operation of the factories, but even beginning of the just morning. So this is surrounded by yellow or orange colored gases. So I was so surprised. That's my the very shocking memories. So anyway, because of this air pollution, many people suffered, and the number of certified patients by government is 2020, but many people believe there are much more people suffer from the air pollution. And also, there are other public hazards and contaminants in Japan. So, it used to be point source, just like Minamata or Itaita disease, but recently it moved to the no-point source pollutant. And the pollution level is not so severe, but very widespread. And the countermeasure is becoming more difficult and more difficult. So that's the other problems. Yeah, there are also many diseases. Just I want to skip here. And in 1960s, anyway, we decided the environmental quality standard, and we made many laws to protect the people. Before this government, I mean, before this parliament meeting, so in our law, they said we also need to consider the economical conditions, not only the health of people, but we should also consider the economical conditions. But before this parliament meeting, and no, after this parliament meeting, we changed. We deleted the part for part of the concerning the economic conditions, and we decided the health of the people is most important. So this year is a very great era for Japanese. Anyway, so we have many also problems here, and yeah, serious public hazards were apparently decreased in Japan now, but we are exposed by various kinds of chemical substances in low concentrations, such as dioxin, pesticides, persistent focus, and some heavy metals, asbestos, and artificial food additives. I should say artificial food additive is not good. Also, it is also very effective and keep people healthy, keep people healthy. But some of the artificial food additives have problems. And most of their potential adverse effects have not been clarified yet. So this is the problem. And I think maybe developing countries may experience all Japanese public hazard history in a very short period. I mean, about 50 or even 100 years ago, our public hazard problem or public pollution problems began with the point source. And we made the countermeasures taking about 50 years. And then now the pollution is moved to the non-point source and widespread problems. And now we are doing also the countermeasures. So we took about 100 years to make countermeasures. But now I'm afraid you are suffered from not only point source but also the non-point source at the same time. So you must work very hard and yeah, you must work very hard. Environmental engineers must work very hard compared to our situations. Also, other hazards like exposure to chemicals, so carcinogens around us, there are many carcinogens, and also the other types of health damage such as birth defect and damage to nervous and the immune systems, those are also the possibility of the effect from the chemicals. And not only the pollution, but also accidents. Sometimes we have great problems. But this is the very notorious the accident. The worst example of that is hazard biochemicals. The industrial accident at Bhopal in India. Do you know this accident? Have you learned it? No, not yet. So poisonous gas escaped from the chemical plant and killed 3,000 people. So according to official estimate, so but many people believe there are more people died from this poisonous gas. So this is the photos of the accident of the Bhopal, and many people died, and many children died because of the poisonous gas from the chemical company. Biotoxic chemicals. In this case, that is the radioactivity. But in case of radioactivity, many people are afraid of radioactivity greatly, but officially, no one was actually killed by the radioactivity. So many people suffered from this accident, and many people had to evacuate or escape from their home country, hometown. But no people died because of radioactivity. So we are also afraid, many people are afraid of the radioactivity too much. So it is necessary for us to understand the level of the risk or level of the toxicity of the pollutants, theoretically or logically. Okay, these are the example of the environmental pollutions and accidents or incidents in Japan. And from now, I begin, I begin the just normal lectures about environmental health assessment or environmental risk analysis. So first is the role of environmental engineers in risk analysis. So why engineers should have the uh, should take care of the risk, or especially health risk. So some people say health risk is that it's a work of medical people or medical doctor. So, but also environmental engineer is also very important for the health risk assessment or to keep the people healthy. Because, okay, now, three necessary informations for risk evaluations. One is the type of toxicity, what is the target hazard for evaluation. Sometimes people say it is the toxicity assessment or something. And those response relationship, how much or how long and what past exposure can make effect. And the third information is the exposure condition of target group, or exposure assessment, we sometimes call it. So after this process, we can carry out the risk evaluations. Risk evaluation means that risk is greater than the criteria, or we must take special movement to protect the people. Or not. So that's the risk evaluations. So, but this information is necessary for the risk evaluations, for risk assessment. All of these processes is called risk assessment. So this information is necessary. So about the toxicity, yeah, medical people are very good at studying the toxicity. And about those response relationship, yeah, of course, medical people are also good at it. But standpoint of the finding the relationship of those response relationship, or the standpoint to find the effect of some of the pollutant is a little different in case of the medical people. That's our experience. So especially for the risk evaluation or risk assessment, we want to know the effect of some pollutants some pollutants have some effect to human health. They don't care about the quantity. So just they say, yeah, this chemical has effects to your brain or something. But not the relationship, or not the response relationship. So now, or recently, my recently means about 30 years ago or 40 years ago. But also engineers began to get this information by themselves. So we also carry out the cell experiment or also the even animal test using animal test. So we try to find the response relationship by ourselves. So I think maybe about those response relationships, medical people and the engineers is about half and half. And about exposure assessment. So medical people don't care about it. Well, they are not so good at the evaluation of the exposure. So this is the main work for the engineers. So because for exposure assessment, we need to carry out for example, the computer simulations or also field experiment or field investigations. But medical people are not so good at those studies. So I think, so especially exposure assessment, so environmental engineering is very important. And and also engineers are very important for the total process of risk assessment. So I want you to also understand what is risk assessment and how toxicity of the chemicals to be evaluated. Okay, from here it's just start of the introduction or basic theory of the risk assessment. First is chemicals to be considered. I think maybe you can imagine, and I don't want to use long time to explain here. So not only I don't want you to forget is not only artificial chemicals, but also natural chemicals also can be toxic. So some people, some people have the, even I should say, prejudice, or just they are afraid of the artificial chemicals. But also, some of the natural chemical is very toxic, and you should be also take care of it. And of course, maximum chemical substances which we take constantly is the food. So food can be also, you can also say food is also chemicals. So some people say, yeah, natural food is always safe, and artificial chemical is always bad or always toxic. But it's wrong, completely wrong. And but of course, the new chemicals or artificial chemicals has the also great problems because our body is not so good mechanisms about the new chemicals. So and about the new chemicals, this is the chemosynthetic history of the chemosynthetic industries. So they say it begins about where they know. I think it's about 150 years ago. Yeah, just artificial dye is produced accidentally from the aniline, which is an ingredient of the coal tar. By Keppel, but they are also very famous chemists and art. And we call it the aniline purple or more. And a big success of the product, we call it the mood decay, and we call it the birth of the synthetic dye industry. And now tens of thousands of synthetic organic compounds are produced commercially today. So, but yeah, they say that's just the beginning of the active chemicals. And in the end of the 19th century and to World War II, the basic ingredient shifted from the coal to oil. It is in 1940s. And at that time, so most of the hydrocarbons are important as a non-aqueous solvent. And but they have a great weak point. But disadvantage of high combustibility, or sometimes it becomes the explosions. So, but hydrogen of hydrocarbon was substituted for chlorine, and the hydrocarbon was converted into a low flammable chlorine compound, keeping the function as the non-gas solvent. So this is the birth of artificial or chlorine compound. So at this era, so many people believe this is the green chemicals. It is very safe and yeah, uncombustible and very safe. And but it works very well. So many people believe this is the it's one of the green chemicals. So 1940 to 1950, such solvents began to be used widely by organic chemical industry and other industries. And the risk of a fire and explosion decreased, but the possibility of environmental pollution increased, as you know. So the industry do not have such argument at that time. So at the beginning, they never thought these chemicals as the bad effect to the environment and bad effect to human beings. So many companies are considering how to balance safety and convenience even now. So we now recognize that we should not use it until we understand its influence on the environment demand. So this is also the role of the environmental engineers. Not only environmental engineers, also chemical engineers or some kind of engineers. But anyway, not only medical people, but also engineers must work today to find the effect to the environment or effect to the human health before commercialization. And the materials which is produced now, just want to skip here. Anyway, so many people are now exposed to chemicals, many kinds of chemicals. And here, this is the move about the move. So the artificial dye, aniline purple. It is produced in 1856 and 1895 is about 40 years later. Bladder cancer in conjunction with this dye was reported by Bain. This is the name of the doctor. So it takes about 40 years to find the health effect of the one chemicals. Now, dozens of new compounds are registered every hour, and approximately 500 are commercialized every year today. So we have many new chemicals, but we must take care of these chemicals. And not only artificial organic chemicals, but also inorganic chemicals also has many problems. So there are many, this is just an example of the heavy metals, and these are the usage of heavy metals, and these are his hazard. But not only hazard, but also some chemicals must be essential. So it depends on the quantity you take. So just you shouldn't say, yeah, copper is very copper is dangerous because they have the health hazard. But at the same time, copper is necessary for your function of your body. So we shouldn't forget it. The problem is the dose. I will explain later, but not only the toxicity or hazard, but the dose is important. So anyway, so also in chemicals is also some problems. The second one is the exposure pathway. How are people exposed to chemical substances? This is just a figure to symbolize the movement of chemicals. The chemicals is released to the environment and go to the forest or the crops or the soils, and also the animals eat some weeds in the soil, on the soil, and also water is polluted with chemicals and accumulated in this, and people eat or drink, eat with fish or drink the water, and even inhale the air. And some rain contains some chemicals in. So there are many passes, other passes. So what kind of passes we should consider? This is the type. This is the theme of this part. I made this figure. But when I first made this figure, I write here toxic chemicals or toxic chemicals or organic chemicals or something. But the people or engineers or professors of the another department complained about it. So not only it is just like all chemicals is toxic. So it feels that it shows just like all chemicals is toxic. So never think toxic chemicals or something. So now I just write just chemicals. So this figure shows just a movement of chemicals, but not only toxicity, but even it is not toxic, chemicals move in the environment, and also we got the exposure from those chemicals. Even it is not toxic. There are many exposure passes, and also the medium which contains those chemicals. Intake of chemicals around us, and we can imagine the water you drink and the air you inhale, and food, of course, you eat. So we are supposed to chemical substances through many products to use at the also workplace and home and recreations, and also cosmetics, pharmaceutical products, and the materials to dye clothes or fuel and smoking. So there are many things, not only water, air, food, but also other media which contain the chemicals. So there are many exposure passes. So we need to consider those passes. Not only water, not only food, but we need to consider many passes. So medium is the means of transportation that will let a chemical substance coming in contact with the human body. So for example, the water, soil water. And in case of the direct contact such as cosmetics, it itself is the medium. And it is important to understand the path that chemical substance moves to the medium, which finally causes exposure to the human body. The typical method to understand it is examining the movement of the chemical substance going along various medium in environment. So this is an example of the very simple and short path. The toxic ingredients include move from merely food to mouth. So in medium is food, so you just eat it. It's very simple. And it is very easy to evaluate how much chemicals you eat or how much chemicals you take. But there in many cases, actually in many cases, real path is more complicated. For example, lead gasoline. Now, I don't know the situation in Indonesia. Now uh, the lead in gasoline is banned already. Okay. So, but even lead in gasoline is banned, but even now, a small amount of lead is contained. And also, lead in soil, which is disposed about 20 years ago, or 30 years ago, still has some effect to the parts of the lead from the soil to human beings. Anyway, lead in gasoline, so found and it goes straight into air, and it is precipitated on field, and lead in soil dissolved in water. It is absorbed by the roots of the corn, and lead is concentrated in grains, and the corn is fed to the cattle, and lead is secreted in milk, and the people drink this milk and are exposed to lead. So this is just only one example of the past. So about when we made the exposure assessment, for example, the gradation schema, some of the gradation species in my laboratory made the research about the exposure assessment of some chemicals. And other times, so they disturb the many exposure paths just like this, or scenario, which they can imagine. All paths which they can imagine. These are for many passes. And they select which one is great pass. So anyway, so at first we need to consider the passes, many passes for our research, for our exposure assessment. So it's the work of the imaginations. But anyway, so students must carry out the stuff of the all passes which they can imagine at first. And also, style of exposure is also important. Main style of exposure is intake or inhalation or transfer. So if you eat some chemicals, it is the style of exposure intake. So some people, especially for example newsletter or TV news, don't care about the exposure path. So it can be also a source of the misunderstanding of the public people. So some of the environmental standards based on the just in some cases just on the intake exposure. But another environmental standard based on the just inhalation exposure. But sometimes those standards are used misunderstanding. So mistakenly they are used. So that's also a problem. So based on the style of exposure, also effect to human health is different. And always, all environmental standards have the background of the assumption of the exposure pathway and the exposure of the style. So never forget. Also, the style of exposure is important for the evaluation using the environmental standard. But in many cases, main exposure path is only one for one medium. We call it the critical path. Yeah, we sometimes call it a critical path. And when food is the medium, oral path is the exposure side, and when air is the medium, chemical are moved to the body through inhalations. And yeah, when atmospheric dust is the medium, the small particles goes to alveolus, and but the big one is caught in um, pharynx and or the bronchus and is gathered in the mouth and swallow. It means even through inhalations, it can be source of the intake exposure because it goes to the GI tract, it goes to the stomach. So the single medium, in case of this example, the air brings two exposure sites. This is the example of the single medium brings two exposure sites. When exposure is discussed, it is necessary to think about the possibility of such exposure styles. So you must have the ability of good imaginations for these variations. You need to imagine many passes and the exposure styles for exposure assessment. Don't think the exposure pass is just only one or just only two or three. There are many possibilities, and if you forget to consider those passes, sometimes you misunderstand the level risk of some chemicals. Okay, this is the uh, very important word in this analysis. Dose, very basic but very important word of dose. And also, this word is misunderstood by many people. So the example is 1 tablet of aspirin contains 325 milligram of pharmaceutical ingredient. So adults usually take 4 tablets per day, and the quantity of aspirin taken per day is so 4 times more, so 1,300 milligram. So some people think this is dose, but this is not a dose. This is not a dose. So it is necessary to divide intake quantity by body weight to clarify biological influence. In this case, reaction of the aspirin. So, for example, in case of an adult weighing 65 kilograms, so 1,300 divided by 65 is 20 milligram per kilogram body weight. And also, it is important to know the period when the medicine is taken to judge its effect. So, in this case, the period is 1 day, so therefore, it is 20 milligram per kilogram body weight per day. This is the typical limit of dose. So, because chemicals distributed in your body, all over your body, so depending on your weight, so the concentration of each chemical surrounding some cells or surrounding some organs is different depending on your weight. So if you take the same amount of the chemicals, but your weight is very small, so in that case, the concentration around your organ or concentration around your cells is higher than the people who are very fat or something. So anyway, so those must be the quantity taken must be divided by weight. So never forget it. When we say dose, it means that is the number which is divided by weight. So, but some people also misunderstand this. But the important thing here is when a child weighing 20 kilograms takes the same quantity as an adult. Dose is 65 milligrams per kilogram body weight per day, which is 3 times more than that of the adult. So if they take the same amount of chemicals, but if their weight is just 1/3, it means the dose becomes 3 times more. So even if the same quantity is taken, the dose is bigger for a lighter person or especially children. So sometimes we should care about the children, especially young, because usually dose is bigger for children compared to the adults. So even some newspapers or some news on TVs use this word mistakenly. So if you think, if you know the true meaning of those, I think you are some of the professionals of the discovery variations. This is just an example of those calculations. The groundwater is polluted with trichloroethylene. Its concentration is 2 micrograms per liter. And the people here is assumed that adults drink 2 liters of water and children drink 1 liter per day. This is the standard value for Japanese. I don't know what value you use in your country, but this is the standard value for Japanese. So at first, quantity of triglyceride which goes into the body is calculated. In the case of adult, this is the concentrations and this is the quantity of triglyceride. So 4 microgram per day, this is the quantity of the chemicals they take every day. And in case of children, so they just drink half. So this is the quantity taken by the children. And those, in case of those, if the adult weight of the adult is 80 kilograms, we must divide it 4 by 80. So those becomes, now we change here the unit to microgram to milligram. So 0.00005 milligram per kilogram body weight per day. This is the dose for adults. So in case of the children, if weight of that children is just 10 kilograms. So the dose is the 0.0002 milligram per kilogram body weight per day. So it's 4 times more. So the children drink less, but their dose of triglyceride is 4 times more than adults. It is important how many, also, it is important how many days the dose lasts for health risk expressions. Yeah, so usually when we decide the environmental quality standard, we made some assumptions. Usually we made assumptions, we continuously take these groundwaters every day for a long period, even for 50 years or even for 70 years. So those assumptions is also very important. Some people don't care about it. So some of the standards based on those assumptions, they continuously drink this groundwater every day for a long period, for 50 years, for example. But some people are very afraid if they take just these groundwaters just once, even if they drink this groundwater just once, there is no problem. No effect to the human health, because this environmental standard is based on the assumption of the continuous drinking of the groundwater. But some people don't consider those assumptions or those conditions. So it is also the misunderstanding of the level of risk. And the important factor to decide toxic strength is dose and period. So this is a dose, yeah, the quantity of chemicals taken every day and taken by the unit weight, but also period is also important. So never forget. This is the example of the calculation of the dose. So it is necessary to know the mass of the chemical substance which comes in the body through each pass. In case of water, it is easy. Concentration in water times volume of water a person drinks per day. And in case of air, also concentration in air times volume of air a person breathes per day. For example, it is in case of the inhalations. Employee of the gas service station is exposed to CO, and the concentration of CO is the 2 milligram per cubic meters, and the labor works there for 8 hours per day. He usually breathes in air for 10 cubic meter for 8 hours. So this is the amount of the CO, and he takes in 8 hours. And if exposure of CO can be ignored at the other places, so this is not only the amount of the CO and he takes in 8 hours, but also this is the quantity he takes in 1 day, for 1 day. So it becomes 20 milligram per day. So if his weight is 80 kilograms, his exposure dose of CO is divided by 0.25 milligrams per kilogram per day per day. This is the how to calculate the dose of some chemicals in case of the inhalation. And also in case of food, yeah, but in case of food, the calculation is usually more complicated. People eat different quantity of different kind of various food. So in case of air, everyone breathes the same air. So it is easy to evaluate the exposure of the old people. But in case of food, so each people eat each quantity of the food and each some people eat the meat and some people eat just rice or something. So it's more complicated. Example is if a kind of perspective is used for apples, this is the case of the difference of the quantity of the eating quantities. The information necessary for calculating those of the perspectives, mean consumption of apple by a person in this country is 40 grams per day. I think this is the number of the USA. I got this number from the Excel book of the USA. So in case of Japan, we don't eat apple so much. And should we think about the persons who eat more apples than average? So just 10% of people in this country eat 140 grams of apples per day. So it is necessary to think about the self of the people exposed to a chemical substance, the average. But how much we should think about those people? So usually, or we sometimes, or I think we often use 95 percentile value for evaluations. So if there are 100 persons, and we decide the quantity of consuming in case of apples or some vegetables, for example, we decide we run those 100 persons, and we select the fifth person who eats who eat biggest, who eat biggest, and we use that values. Not the most, not the biggest each person, because it is sometimes it is rather extraordinary, and it is sometimes it is very extraordinary. For example, in case of USA, I heard some people drink Coke, about 20 cans of Coke every day. So if we decide the standard of some kind of the additives in Coke by his depending on his numbers, maybe we must decide very severe criteria. And it is not so good. Also, economically, it is not so good. But too severe, we must decide too severe criteria, or too severe standards. So, yeah, also, of course, it is important also to protect the people who extraordinarily eat some food. But sometimes, yeah, it is too much. So it is a decision by the governors, or it is the decision of the governors or local government or central government. But we don't select the extraordinary consuming people, but usually we use the 95% values. 95 or 5% biggest values we use. But in another case, also some people say we shouldn't take this number because in case of the Minamata disease in Japan, so fishing these people in Minamata were thought to eat 10 times more fish than average in Japan. So if you consider just the risk of Minamata disease, it is very localized in limited area. So in those cases, you should use the number of the people living there, not the average in Japan or not the average in the world. So if you concentrated on some kind of special effect or special disease, for example, you should use the number of the people there who may suffer from that disease. So in case of Minamata, we should use about the fish consumptions. We should use the number of the 10 times more than the average in Japan. So not only 5% value is okay, but also we need to consider the situations of the people who are suffered from some chemicals. And it is insufficient to get the information of the quantity of consumption of food and its distribution in the population. The dietary habits of the people change with time. Also, yeah, this is also another problem. For risk evaluations, now we have the statistics of we use the statistics of the consumption of food. How many grams of rice they usually eat, and how many liters of water from tap water they drink. We use the statistics, but some of the statistics usually as a whole. For example, in case of Japan, about 30 years ago, they eat rice, maybe how many grams? Several hundred grams per day for one person. But recently, it decreased because many people eat bread. And and also about the tap waters. About 30 years ago, in Japan, about 30 years ago, many people drink tap water directly. But recently, very few people drink tap water directly. Many people just drink the mineral water, bottled waters. So it changed great. It changed great. So also we need to consider the change of these numbers. And without enough data required by statistical study and risk assessment, scientists are forced to give different answers. This is a great problem. So always governors say, so what? I say, so what? So they just want to know if the situation is bad or situation is good enough. But the scientists, we know we don't have enough data. We don't have enough data. But it is no use to say we don't have enough data, so we cannot make decisions. So we can make we cannot decide how we should do. But the governor always forced to do something before the deadline. So also scientists must make some decisions with the not enough data. That's a great problem. So how we should make the decisions is also another problem. And maybe about the risk communication, about the risk management, we can, I think, I hope I have some example of the decision making. But the problem is it is very difficult to get the enough data for risk evaluation, which is also the problem. Is it okay to continue with the lectures? Okay, and how to know the concentration of chemicals in food? This is also another problem. Some people say, if you want to know the concentrations of chemicals in food, yeah, it is okay. It is easy. You can just measure it. But it's not so simple. It's not so simple. Okay, there are two methods to know the concentration in food, for example. In case of artificial addition of chemicals, in case of it is very simple. Food additives, addition of chemicals can be controlled carefully, and we can know the concentration of precisely by calculations because we add that chemicals to food. We know those numbers. And the concentration of environmental samples, but in case of concentration of environmental samples, the measurement is necessary because we didn't add the chemicals intentionally. So measurement is important. Example is in case of the pesticide, pesticide is applied to vegetables and the manufacturer must perform examinations in conjunction with the effective quantity of drug and the residual quantity in the vegetables that can prevent toxicity from people. So, because these conditions, they must measure the concentration of the pesticide in food. Because we are so sure, they just use pesticide to soil vegetables on the plant. So, but they're not sure how much pesticide transport to the vegetable itself. So the manufacturer can acquire the authorization to sell this pesticide if the government accepts that the residue of the pesticide is enough. So they need to measure. To know the relation of application and residue, the measurement is needed. But measurement is needed, but it's not so simple. We can know it by the real measurement or can estimate it from quantity of applications theoretically. But this kind of estimated calculation is usually very incorrect. For the accurate calculations, it is necessary to know how much of residual pesticide is contained in which part of the vegetable. It is also necessary to understand how much drug is lost by a physical process such as rain and wind during cultivating vegetables, and the chemical resolution speed of the pesticide in the vegetable field, and how much pesticide remain in food when the vegetables are cooked. Some people forget these variations. Also, cooking can decrease the concentration of the pesticide greatly. So the calculation is very difficult. So it is much easier and reliable to measure the quantity of residual concentration directly than to calculate it. So real measurement analysis is necessary. This is another example. The concentration of benzene in the air of service stations, or arsenic concentration of groundwater flowing through the disposal site. So also this concentration can be calculated depending on some assumptions, but those assumptions is rather incorrect, so sometimes it is much easier to measure it directly. But also I would say the also measurement has some problems. Concentration estimations using the models or calculations about the calculations. The third method to know the concentration of the chemicals in the environment is use the model. I'm sorry. So here is just accurate calculations. Accurate calculations. But for accurate calculations, we need many data. We need many data. But yeah, transportation ratio from soil to vegetables or any other many parameters. But it is very difficult to get those parameters. And also the measurement is also, of course, but maybe next slide. Yeah, next slide I can explain, but sometimes the measurement has some problems. And also usually it takes money, more expensive. And the third method to know the concentration is the model evaluations. A good example is the case to estimate the atmospheric concentration of the chemical substance released from factories. At first, the information about the limited quantity of the chemical substance per hour is given. Yeah, we want to know this data. Then it is substituted to the mathematical models for expressing the physical process of the spread of the chemical from the source. So especially in case of air pollution, it is very difficult to measure the concentration of chemicals in air because air is everywhere and spread easily. So, okay, yeah, you can measure the concentration of chemicals in air here, but we are not sure you can use the same value for another place. So, but of course, money is limited and time is limited. We cannot measure everywhere. So, the representativeness of the measurement value is also the problem in case of the measurement. But in case of the estimation based on the model, we can estimate the concentration of some chemicals everywhere. So it is also very efficient. Even it is incorrect, sometimes it is more efficient than actual measurement. So, okay. So then, properties of the target chemical substance and data of the atmospheric and climate conditions are substituted to the model to calculate the concentration depending on the distance from the source. So from chimney, how pollutants spread, and how much is the average concentration of the chemicals in the air surrounding